Let's do some more calculus review. So Calc 1 review. This one is what I'm calling part 3. I'm actually kind of going backwards in a course. So first question, this has to do with some limits. So limit as x goes to 5 of 3x minus 5 over x plus 2. So initially just try putting the numbers in. See if you get a good answer, a real defined answer. 3 times 5 is 15, minus 5 is 10. 5 plus 2 is 7. You get 10 sevenths. That's it. That's great. Next question. The limit as x approaches 5 of x squared minus 10x plus 25 all over x squared minus 5. Now I'm going to do this the traditional way. You might notice that L'Hopital's rule applies here because you would get 0 over 0. And so you could use L'Hopital's rule. I might do that later. But initially I just need to factor. Now I'm assuming that you can maybe see that this is 0 over 0. If you can't, you might just test 5 in there and you will get 0 over 0. But x squared minus 10x plus 25 is x minus 5 times x minus 5. It's a perfect square trinomial. This is a difference of squares, and it would be nice if I would have written the problem correctly. Here's the problem. It's 25. So this is x plus 5, x minus 5. So it really wasn't the right problem at first, but it should have been. Okay, so I can factor, cancel, and then I try plugging the numbers in. 5 minus 5 is 0. 5 plus 5 is 10. 0 over 10 is defined. It is, in fact, 0. Now let's try L'Hopital's rule, just to give you a practice on that, and you might like that better. So this is the limit as x goes to 5 of the derivative of the numerator. Notice this is not the quotient rule at all, but 2x minus 10, 2x minus 10, all over the derivative of the denominator, which is 2x. So let's stick 5 in. You get 2 times 5 is 10, minus 10 is 0. 2 times 5 is 10. You get 0. So either way works. That does qualify as L'Hopital's rule. Now, next problem. Let's take the limit as x approaches 0 of sine x over x. You likely had this one months ago, and this has to do with the squeeze theorem, and you may have tried that. Let's try this with L'Hopital's rule, because if I put 0 in, sine of 0 is 0, x is 0. So let's use L'Hopital's rule. So this should be the limit as x approaches 0. Write the limit every time until you actually get the answer, okay? But derivative of sine x is cosine x. Derivative of x is 1. So L'Hopital's rule worked. Throw 0 in, you get cosine of 0, which cosine of 0 all over 1. Cosine of 0 equals 1. So L'Hopital's rule makes that one quite nice. Let's try some more. Let's take the limit as x approaches infinity of x plus 2 over 5x minus 1. Now L'Hopital's rule works here because this would be infinity over infinity, so it's an indeterminate form. But the traditional method is to take everything in here and divide by x, divide by the highest power of x in the whole problem. So if I do that, I end up with this limit. X approaches infinity. X over x is 1 plus 2 over x. 5x over x is 5 minus 1 over x. As x goes to infinity, this one goes to 0. This one goes to 0. I end up with 1 over 5. So there's my answer to that one. Now, like I said, L'Hopital's rule works fine there, and you could certainly use it. If we do that, we'd have the limit as x goes to infinity of 1, that's a derivative of x plus 2 over 5 equals 1 over 5. So you might find that a lot easier. Now, I'm going to change gears a little bit. Let's find an estimate for the square root of 48. This is a differentials, so using differentials. This is kind of a nice scenario, and you have to use it in other calculus classes as well. So what you do, first of all, find a function that relates to this. So f of x is square root of x. That's a function that relates to it. And then find an exact value. So if x equals 49, then f of 49 equals 7. I know that one, so that's a good thing. Now, how far from 49 is 48? That's going to be delta x is equal to dx. And to get from 49 to 48, I have to subtract 1. So there's the setup. Now, here's the deal. We say that f prime of x dx is approximately equal to dy. Okay, it actually is equal to dy. Hang on a second. Okay, it's literally equal to dy, but that's approximately equal to the actual change in y. There we go. Get the approximation in there. So what I'm going to do is I'm going to take this and put it together. Okay, so dy, because we're going to find dy, that's the estimating part. So dy is equal to, well, what's f prime? It is the derivative of x to the 1/2, which is 1/2 x to the minus 1/2. And then multiplied by dx. Okay, so dy is equal to 1/2. What's x? Well, x is 49. So 49 to the 1/2 power is 7. Negative makes it 1/7. And then what's dx? dx is negative 1. So this is negative 1 over 14. So that's how far y changes from what it was to what it is. So our estimate is this. It is 7, what we had for the original when x was 49, and then minus 1 over 49. Okay. If you put this in fractions, you could take 7 times 49. Well, okay, so that is what? 343. So it is 343 over 49. Minus 1 over 49 is 342 over 49. So let's check this out with a calculator. First of all, I'm going to take 7 minus 1 over, that was over 14, wasn't it? Whoa, 14. Okay, let me reframe this, because I did that wrong, didn't I? Okay, so 7 minus 1 over 14. I don't know where I got the 49. Well, I do know, but then I wrote it again, 14. Okay, so 7 minus 1 over 14, duh. Now, change this to 14s, okay? So 7 times 14 is 98. So we've got what, 98 over 14 minus 1 over 14. This was way off base, wasn't it? 97 over 14. Okay, so I'm going to check that. So 7 minus 1 over 14. Good thing I was checking my work. So it's about there. If I look for fraction, I get 97 over 14. Okay, so there's the right answer. Now, let's check compared to the calculator estimate for the square root of 48. So I'm going to take the square root. Yeah, right. Okay, square root of 48. So 6.9282, etc. Look at this. It agrees until the 4th decimal place. So pretty easy way to look at that.